Hello, everyone. This is for next Monday, November 21st lecture. So first of all, let me share my lecture file, lecture PowerPoint file. So ENES240, Chapter 6. First, summary of previous lectures, related lectures, and then first of all, accuracy is the reference value minus calculated value, and the precision is how densely it's accumulated, that one. So absolute error is true value minus approximate. So true percent error you can calculate, and then relative approximate error is when you don't know exact true values. At that case, how can we calculate errors? So at that case, approximate error, epsilon A, we denote as epsilon A is present approximation minus previous approximation divided by present approximation multiplied by 100. So this is the approximate error, percent approximate error, epsilon A. So root, what's root? When fx is a function, and at that case, any m that makes fm equal 0, at that case, we call it zeros or root of fx. So we already know this. And then how can we calculate root of function fx? So several different ways, as we know. And the first of all, graphical method. And then second one is bracketing method. And bracketing method is we set initial 2 point, like here and here. And then using the 2 point, and the sign of that two function is one is positive, another one is negative, because root is between that 2 point. So, and then first of all is bisection method. Let's assume we select initial 2 point of x lower L and x upper xu. At that case, next point we set as center of this 2 point, and then calculate, check the sign of each fxr, fxu, fxl, and then one should be positive, another shouldn't be negative one, and then set the next point. In this case, xr and xu can be the next point, and then xr is new xr is now the 2 point of this old xr and the xu, and then set the point, and so on. That's the bisection method, as we know. And then how can we set the number of iterations? We can derive this one. This equation is only available for bisection method, and other method, you cannot apply this equation for other method. So, and then EAD, desired absolute error, is like n equal log 2 EAD delta x divided by EAD. So I showed you how to derive these equations during the lecture time. So I assume you guys remember this. And then next method is the force position method. And the force position method is how can we calculate an initial point xl and xu, we select and then calculate fxu and fxl. At that case, if we know 2 points, we can derive first order equations, y equal ax plus b, and that one, using that equation, we can calculate y equal 0 point, and that point would be our next xr new point. And then rest of it is similar to bisection method. We can check this sign of fxr and fxu and fxl. So multiply by fxl, multiply by fxr, and check. One should be positive, another one should be negative. So at that case, in this case, xr would be xr and xu would be our next point. Because fxr is negative sign and fxu is positive sign in this case. So, and then go forward. That's the force position method. So it's the previous lecture we learned, and then chapter 6 is open method. What's the, or before that, Wegerstein method we learned. And then this one is y equal ax. We can calculate y equal ax graph. And then we calculate the next point. 45-degree line. It means y equal x. And the tangent 45 equal 1. So the derivative of this first order equation is 1. So we can calculate the point. So, and then root of equations is briefly, it has 2 methods. One is bracketing method and the bisection method, force position method, and the Wegerstein method. And that's the bracketing method. And common thing of this method is we need initial 2 points. However, another method, open method, is we need only 1 initial point. Okay, only 1 guessing point we need. And then what's the advantage? So it can, when it converges very fast because we need to calculate only 1 point, 1 instead of 2, bracketing method. However, it's possible to not converge. It's diverse. It is more possibilities. That's the disadvantage of open method, so, as we know. And then there's several methods of open method. And first one is simple fixed point iteration method. So, and then when we have y equal fx graph, and then rewrite the equation to fx equal gx minus x. So at that case, solve fx equal 0, it means gx minus x equal 0. Gx equal x. What does that mean? We have 2 different graphs. One is y equal gx, another one equal y equal x, and then its cross point would be our desired root point. That's the fixed point iteration method. x0, first point, and then y2 equal gx, and then is y equal x graph, and then x1 is our next point. And then it's another point is x2, and so on. It's our desired root. root point is this cross point. This would be our core root. So another second method, open method, is Newton-Raphson method. And this is how can we calculate. And so at first, initial point, we get initial point of xi, and this one is, at this point, we know y equal fx. So fxi, we know, and then first order derivative. So f prime xi, we can also calculate. Then what? F prime xi equal delta x, delta y divided by delta x. And the delta y is what? Fxi minus 0. This would be the delta y. And the delta x is xi minus xi plus 1. This would be the delta x. And this would be the delta y. So using this equation, we can calculate xi plus 1. Xi plus 1 equal xi minus fxi divided by f prime xi. This is the Newton-Raphson method. You know, algorithm, yeah, okay. Using that. However, this Newton-Raphson method, it says first point, initial point is, and then 1, 2, and 3 point. And this is Newton-Raphson method. However, it's not always converge. Sometimes it's diverse, okay? If it's x0 equal, x0 point is here, our root is here, but as x1 is here, x2 is here, and x3 is somewhere here. So it's not converge, it's diverse. So it can be, it's disadvantage of open method. So second method is, as we know, instead of using first order derivative, we can use h, f x0 plus h minus fx0 divided by h. And h is a very small numbers. At that case, we can derive, instead of using f prime x0, we can assign here fxn plus h minus fxn, h fxn. So in this case, we don't need to calculate first order derivatives. And then that's the disadvantage of this second method. So, and the modified second method is, instead of h, we can calculate h as delta xn. Delta is a small perturbation fraction. So in that case, we can calculate this xn plus 1 as using these equations. That's the modified second method. And then MATLAB support its functions, actually two functions. One is f0, another one is a root. And that two functions is can be used to find root. So exercise 1, exercise 2, exercise 3, and 4, I believe you guys already did it during the lecture time. And the exercise 5 and the second method using MATLAB script. So this one is basically second method equation is this one. So xn plus 1 equal xn minus f, xn plus h minus fxn, h fxn. So this is how we can implement this one. So, and this one is in this part, okay? And this part, and error calculation part, and so on. So, and this is the calculated root values. And exercise 6 is same equation, however, using modified second method by hand. So in that case, we should know delta, and the delta values 0.01. So x0 equal 3.5 and delta equal 0.01. So in that case, modify the second method is equation is this one, and the implementation is you guys can calculate using this equation, and x0 equal 3.5, fx0 calculate, and the delta is also assigned, and so you can calculate this. And second iteration, okay, third iterations using the modified second method. So, and the Taylor series, no, that's a mistake. So exercise 7 is like determine the highest real root of same fx equation using MATLAB function. As I explained, it has root. We can use root or f01. I used the root functions. So in this case, we need first 1, -6, 11, and -6.1. Using this one, implement root A, and then command window, we can get all root values here. So this is the end of chapter 6. So if you guys have any question about chapter 6, you can email me, and then I will answer for it my best. So and then another one is I upload homework number 7. So here homework, yeah, and this one homework number 7. So it's determine the highest real root, okay, not lowest one, highest real root of the below function by MATLAB script. So not by hand. You need to do the programming using MATLAB. Okay, so using graphical method and using Newton-Raphson method, and x0 equal 3.0, and the relative error is this one. Maximum allowable iteration is 50, and so using this one. And the last one is using second method, x-1 equal 2.5 and x0 equal 3.5, and show the final result of percent relative error, root estimate, and the iteration numbers. You need to show this. And this one is due date is 28th, I believe, or 29th. Okay, so after 2 weeks, you need to do this, because next Wednesday is a holiday, so you don't need to submit that one until that time. So that's it. That's all I have for the next Monday's lecture. Again, if you have any questions for chapter 6 and homework number 7, email me, then I will answer for it. Okay. And thank you and have a nice day and bye.